Without further remark, let me present Andrew Whelton. He's an assistant professor of civil, environmental, and ecological engineering here at Purdue. Two of his current research priorities are to develop approaches for better predicting drinking water quality at the tap and safely decontaminating premise plumbing. In 2014, at Governor Earl Ray Tomblin's request, he helped West Virginia investigate the Elk River chemical spill. The spill prompted a drinking water ban for more than 15% of the state's population that lasted more than a week. Professor Whelton has testified at the Indiana Senate, briefed the U.S. Chemical Safety Board, and delivered invited seminars, workshops, and lectures across the U.S. So today he's going to present his talk titled Water Technology Misuse, Flaws and Disasters, the Need for Reinvention. Please take a minute to silence your cell phones, and we'll turn it over to Andrew. Thank you so much.
So I truly appreciate everybody coming for this talk, everybody coming from far and wide, from California as well as the East Coast and some down south as well. I'm going to talk about something that we're living right now. We're living in a time when we have technology that is being used to help us get safe water pipes, help us repair these assets in place, and we need to balance the risks and rewards about how we go about doing this. So as President Daniels mentioned, the purpose of this meeting is kind of balance risk and rewards, talk about the dawn of the technology as well as possible doom if it goes in an uncontrolled fashion. And I want you to keep that in the back of your mind as we go through this talk. Now, water pipes are critical for the security of this nation as well as others around the world, economic vitality as well as the health of communities worldwide. We rely on water pipes, say here at Purdue University, to provide us water in the dorms, to provide us water at the recreation center, to provide us safe water that doesn't make us sick in other places around town. We also, when we go home, we rely on water for the water parks. Just think of the last water park you went to, and maybe it was filled with contaminated water. Would you go there? Right? We rely on these things as very important aspects of our society, and they also provide economic vitality. In order for businesses to thrive, they need water. They need to be able to produce, to manufacture, to allow people to come visit the mall, and other aspects of our society. And health of communities, we've touched about before, and it's very easy to realize what happens when you don't have functioning water pipes when you look at the recent hurricanes. Okay? The recent hurricanes that have affected large population centers of the U.S., including Hurricane Maria, Hurricane Harvey, and Hurricane Irma, basically incapacitated water pipes. They filled them up with water, or sometimes there were main breaks, there was depressurizations. You couldn't get safe water to the buildings, and sometimes the sewage in the sewage pipes mixed with the water. Okay? Flood waters went into sewage pipes, and so we realized very quickly in these types of disasters that we really rely on water pipes to convey us safe water that allows us to thrive. And what you may not know is in the U.S., there are millions of miles of water pipes. Many of these are buried underneath the street or on your property, or they're also inside your homes and inside your office buildings. And these pipes are aging. Many of these pipes were installed in the 1900s to 1950s. And so they're possibly 60, 70 years old. And generally, they're out of sight, out of mind, and we don't really think about it until a wet spot shows up on our ceiling, and we realize that that pipe is now starting to leak. Or what we find is sewage starts spilling out into the bay where we used to go play. And we realize that those pipes are starting to leak and damage, and we need to do something about it. Estimates are that about 40% of all water pipes, these are drinking water pipes, sewage pipes, and water that conveys storm water, rainfall when it rains, away from the roadways, need to be repaired, okay? So in my lifetime and in many of your lifetimes, you're going to be responsible for doing this, you, your friends, and your family. To give you some data, this is a study that was conducted several years ago, and what it was is an inventory of all the buried just drinking water pipes in the U.S., what types of materials these were. The materials were steel, cast iron, some of them were ductile iron. And what I want to bring your attention to is we're past due, right? The bills come. We have to repair or replace these pipes here because many of these pipes from the 1900s to the 1950s are still in the ground, are still in buildings, okay? And these can cause contaminated water. They can promote microbial growth and the growth of organisms and pathogens in our plumbing, and these need to be addressed. Now, an often type of pipe nobody really talks about because we take it for granted is stormwater pipes. When it rains out very hard, the water needs to go somewhere. And preferably, we don't want it to go on the street because we're driving on the street, right? If it goes on the street, you can hydroplane. Anybody ever hydroplaned before? I have hydroplaned. It is scary, right? So we rely on stormwater pipes to basically take that water and send it underneath the street to some other location where it can drain away, okay? But these pipes also are decaying and falling apart. The issue here is that with these pipes, they go underneath the roadways. And so when you have a pipe fail underneath the roadway, you get a pothole. Or you can have it wash out. You can have the roadway wash out. So we have public safety issues. The damage can be catastrophic. And here is the example down at the bottom where we're looking at a corrugated steel pipe. You take metal and you put it in water for 50 years, and with running water, it will erode away. And then what happens is the water isn't going through your pipe anymore, it's going through the soil. And then it's scouring out the soil, and then the pipe can start to mechanically fail. So to address these issues, historically what we've done is we've dug them up. We've dug up these pipes. We dug up these pipes primarily because that's the way it's always been. Anybody ever seen pipes being dug up on their street or nearby? Yeah. It can be a pain. It really can. Because, first of all, they send you a letter telling you you're not going to have water for a certain period. Then they're going to tell you that you shouldn't use the toilet, you shouldn't wash your clothes during that time, right? Because they don't want waste and water coming down the pipe to where there's no pipe, right, generally. Traffic disruptions, try driving a car down that street, right? And so closed roads, rerouting, and safety issues where you have open trenches, where you can have people, bystanders, fall in these trenches and get hurt, or you can have people, even at the work site, dealing with hazardous conditions. So this is how it's always been until the innovation of trenchless technology. Trenchless technology is disruptive. It was disruptive. It still is disruptive. It allows us to basically repair these pipes underneath the streets and in our buildings without having to rip up all that dirt, without having to remove the walls, remove the drywall. And there's actually a world celebration tomorrow about World Trenchless Technology Day. Okay? So you Google it, you'll find the website. It's pretty cool. And one of the most commonly used trenchless technologies in the U.S. is a technique called cured-in-place pipe technology. And cured-in-place pipe technology is the chemical manufacture of a new plastic pipe inside a damaged pipe. So let's say we have a sewer pipe underneath the street. It's cast iron. It looks like Swiss cheese because it's all corroded out. What you can do is you can insert this liner inside one manhole, pull it through the pipe that's underneath the street as cars are driving over it, and go to the other manhole and see this fabric come out. Then what happens is they literally manufacture or cure this fabric into a pipe in place. And it's amazing technology in that it can take 2 hours, it can take several days, depending on how thick the wall is and other conditions. But the fact of the matter is, people can be driving down that street, right? All the while, this pipe is being repaired, so it doesn't cause that type of disruption. You can have different types of resins or chemicals used in the process. You can have different curing methods. You can pump steam into this pipe, this resin. You can pump hot water in, or you can take a UV light train and drive the UV light train through, and the UV light causes it to harden. Okay. This is an installation where the resin tube, this is the resin tube here on your left, the resin tube is coming to the site on a refrigerated truck, because if we have it at room temperature, it's going to harden. So if you drive it, say, across country to the site, it will harden. It'll be hard as a rock, and you can't use it. But these are raw chemicals in here. They take it, they insert it into the manhole, and then they pull it through or push it through all the way to the other manhole. And this is what it looks like after. So here we have a reinforced concrete pipe with what's called a CIPP inside it. So you literally take a saw and cut off both ends of the hardened pipe, and now this is ready to be used. Okay? So it's really an amazing technology. Some people have asked me, how long does it last? I've seen 50 years, I've seen 100 years. We know that CIPPs that have been installed in pipes already today have at least lasted for 30 years. Okay? CIPP manufacturing sites are highly transient. They literally chemically manufacture pipes around town. Okay? There's no street address where they chemically manufacture all the pipes and just slide it into the pipe, the damaged pipe. They literally go from manhole to manhole or side of street to side of street and move during the day. Okay? And once they're done, they pack up and move on. This shows you here a pipe that was repaired in a very busy part of New York. Okay? And what you'll see is trucks and traffic driving up top. And what's really amazing is that when they repaired this pipe, they didn't have to shut down the road. They didn't have to divert traffic. And this was, I think it's a 5-lane highway. Okay? So you're talking about major disruption if you have that happen. So cured-in-place pipe, according to a study that was just released this month, is about a $2.4 billion industry globally. And about 40% of that industry is in the United States. And that's primarily because U.S. infrastructure is so decayed and so deteriorated that we have to do something now. And cured-in-place pipe is the most popular technology being used for repairing this. There's different types of resins that are used globally. There's different types of fabrics that are used globally. And there's different types of curing methods or ways that you cure these products in place. Okay. So one of the questions that's come up with this technology is after you insert, say, this blue liner into the manhole, upstream manhole, and you start pumping steam in, you have these red lines, and that's these emissions of stuff coming out from that material. So think of a sock like a tube sock, right? And if you fill a tube sock up with water, you'll get water dripping out. And that's kind of like what happens with CIPP when it's not cured yet, when it's not hardened. So stuff comes out. And that stuff sometimes exits through manholes, and it also goes up exhaust pipes that contractors sometimes deliberately put there. Okay? And this is what that looks like. And so this is a picture of Philadelphia, downtown Philadelphia, where one of the residents took it for us. This is the fugitive emission from the downstream manhole. And sometimes what happens is because pressure is put into these pipes and steam is put into these pipes, it causes emissions to go up into people's buildings, okay? So into nearby buildings. So the big question for us was, are chemical emissions a problem? Is this a technological issue? And when we started putting some studies together and trying to figure out if anybody has had incidents where chemicals have gone into buildings or caused any health impacts, we started putting together a number of incidents. And most of these are reported in the public literature as well as the media. And so what we find is that for the red stars, these in the last 20 years that we know about have happened at daycare centers, elementary schools, middle schools, high schools, offices, and homes, where chemicals have either gone into the buildings and cause building evacuations or people to complain about sickness. And offices, some have been contaminated for up to 3 months. So these are some of the incidents that we've found. One of the issues with these incidents, however, is that often the people responding to the incidents didn't really understand the technologies or what chemicals could be emitted. And there really wasn't much health follow-up associated with the incidents that we found. There have been some incidents in some places around the country, and those are the yellow stars, dealing with fish kills, surface water contamination incidents, and drinking water contamination when people have used CIPP technology and improperly handled materials or improperly handled the waste that they generated and either dumped it in streams and ditches or other processes. So there seems to be something there. And since July 2017, there have been 4 incidents in the last several months. The most recent happened in San Diego, California, where 36 kids were sickened, and 1 went to the hospital because of the emissions from a cured-in-place pipe construction site. And so you can go online and see these videos. They're pretty eye-opening. But the top 2 are from San Diego, California. There's another one from Dublin, California this year. And then another one here from Nyack, New York, which is right outside New York City. Somebody reportedly needed oxygen in their house because of the vapors that came in from the process. And here's just a list of some of the incidents that we've found. We published a paper, so most of them are listed there. But it's not abnormal to have these types of incidents happen. So then the next question is, what do CIPP companies and cities say about the exposures? And what we've found basically is that contractors and cities have declared the exposures safe, harmless. You look on Twitter and you'll see cities openly saying that it's safe for people, for pets and people. Don't be alarmed, trying to tell everybody not to worry about it. There have been some documents provided to the public that say 50 ppm is a safe exposure level given to a family, and that's completely inappropriate because no child should be exposed to 50 ppm of styrene, for example. The 50 ppm is for workers, adults that work in these factories and such. So this is a picture of a city employee at an eastern U.S. city, and what's important to know is he's not wearing respiratory protection. So the next question is, a scientist, what does the literature say? And when you look back in the last 16 years, only 4 studies have been conducted to find out what materials actually are emitted into the air. So the first study was conducted in 2001, and I want to bring you on this journey because it leads up to where we are today. There were several buildings that were tested. This study was conducted in Canada, and they conducted air monitoring outside at a CIPP site right near the manholes. They put some air sampling devices in people's homes where the chemicals may come in, and the highest level they detected was 3.2 ppm of styrene. This is only one chemical of the many chemicals that are used in the process. Also, some of the issues with this study are that they didn't actually report what types of materials were used to create the CIPP and some other issues. In study 2, there was another Canadian study that was conducted to look at emissions from manholes. And the investigators used photoionization hazmat devices. They took these devices and they put them in the manhole and they watched the signal change over time. They reported, this is their data, they reported styrene was present at about 110 ppm, okay, not 3.2, but 110 ppm. One of the issues with this study, however, is that the device they were using doesn't just tell you it's styrene, it responds to multiple other chemicals. So for example, if methylene chloride was present, the device would respond to that too. And they didn't do any confirmation testing to prove that their signal was 100% styrene. Okay. Study 3 in 2005, a U.S. federal agency got involved, and they responded to an incident in Milwaukee, Wisconsin. And in this incident, the contractor was repairing a pipe underneath the building. The vapors went up into the building, and the building was evacuated twice. It remained contaminated for several months, and the ATSDR declared it as a public health hazard. And finally, there was a study in 2015 that was conducted by a University of New Orleans graduate student and the city of Los Angeles. And what she did was, as part of her internship there, she conducted air testing at 3 different CIPP sites. during steam curing. So when they were pumping steam into the CIPP, she took one sample and sent it to a commercial laboratory to analyze, and her data indicate that over 1,000 part per million of styrene was emitted. Okay? And this red line is what's called the IDLH concentration for styrene, a concentration at which a worker can escape without injury or irreversible health effects in the event of a respiratory protection equipment failure, implying that they should be wearing respirators when they're doing this activity. This gentleman's not wearing a respirator, and she's not wearing a respirator. So based on those data, what we're looking at is, we have this amazing technology, but what are the risks associated with using it? And we really don't know, primarily because a lot of issues are associated with these prior 4 studies, and not much is out there. So there have been some prior studies before what I'm about to tell you in the Purdue study, but the prior studies have indicated that at least a steam-cured CIPP process, which is the most popular process used in the United States, can create this condensate. And this condensate we collected down in Alabama from a site. We exposed it to these organisms called daphnids. So in order to determine how toxic something is, you generally take chemicals and you put these organisms in it, and you go back 24 hours later to see if they're still alive, and you count them. And you go back 48 hours to see if they're still alive. And when we take this condensate and we put the organisms in it, in 24 hours, we didn't see anything. So we did the study several times, and what we found out was that the organisms dissolved away within 24 hours at room temperature. So we believe that the process can generate materials that can be toxic, acutely toxic, and the wastes have to be controlled. So that leads us to a 2016 National Science Foundation Rapid Response Study. And this study was funded by the National Science Foundation to better understand the materials emitted from CIPP, sanitary sewer, and storm water pipe installations. This is a Purdue study. There was about 13 people involved, 6 faculty members, and what I want to bring your attention to is the current industry awareness of the materials that are being emitted indicates that you do not need respiratory protection to be in these white chemical plumes, okay, based on the data that we've seen in the past. And so our purpose was to evaluate what's being emitted as well as the chemical toxicity. And this study has been published. This study came out in July of 2017. It was reviewed by eminent experts in the field that we don't know what they are. The journal, American Chemical Society journals, chose those experts to review this manuscript. It's posted. It's freely available online, so anybody can download it. Okay? And then you can go to cippsafety.org. We set up a website, and people can go there, look for frequently asked questions about the study and such. What are the main realizations of being on a CIPP site that really hit me was you are entering a chemical manufacturing facility. Okay? So typically we create boats, we create these other fiberglass materials in ventilated areas where there's very stringent control, and the only thing you're doing is you're moving a new boat in and a new boat out. Here what you have is you have raw chemicals being brought around to different sites under different pipe sizes, under different wind directions and wind speeds. And the raw chemicals themselves give off a signal. Okay? So there are emissions from these raw chemicals, and that's important to realize. What we see here is the uncured resin tube from the refrigerated truck going into the pipe. Okay? And these are raw chemicals in the fabric that are being fed into the pipe here. Okay, what happens next is for this situation, they pump steam into it, and then on the other side of it, this is what you see. Okay, so this is what's emitted into the air, and as part of our National Science Foundation study, that's our stainless steel unit there. We were grabbing that stuff and trying to collect it to figure out exactly what it is. Okay, and what we found out that it's actually not steam. Okay, it's not steam. It is a multi-phase mixture. It is solids, liquids, and gases. Okay? And this includes particulates, droplets, partially cured resin, and it is not steam. this material here is at room temperature, right here. And this material on top, actually, if you take a little bit of that out and put it on the ground, it will evaporate very fast. And that is because it's pure organic solvent, okay? So that would be like going to Home Depot or Lowe's and getting the acetone from the aisle and put it on the ground. And that's the type of evaporation that you could see here, okay? What we also had, the materials engineers characterized this stuff in here. What they found out was it was actually partially cured plastic. So for steam-cured CIPP, when you have an uncured resin tube in the pipe and you blow steam down, there's force, right? And you're creating plastic, but the force is likely taking some of that partially cured plastic with it and emitted it into the atmosphere or into the work site. And so the multi-phase mixture is not steam. And when we started looking at what compounds are emitted into the air, we found a number of different compounds there at many sites that we tested. Some of these are listed here. Some of them are known hazardous air pollutants, endocrine disrupting compound, and styrene is reasonably anticipated to be a carcinogen according to the National Toxicology Program. Another issue that we discovered on these sites was that chemical emissions can be high and transient. Okay, so what we have here is time on the x-axis, and we have the PID response, or that little hazmat unit. And we had it stationed at one point, and we monitored that concentration over time. And what we saw is when you start the curing process, before you started the curing process, you have a blast of chemicals coming out. And that is because the steam-cured contractors use forced air. So they pump forced air in there, and it basically strips out likely the chemicals into the air and then exit the site. Then they started the steam curing process, and the chemicals were emitted into the air here. And then over time, the emissions decreased. Okay? And then they stopped the curing process, and they switched to cooling down the pipe. So they'll start blowing just air in it, not steam anymore. And this is a function of location, wind direction, and worksite activity. Okay? One question here. So if you're going to say, well, I need to know what the maximum concentration is for exposures, what do I need to be worried about? If you go out like past studies and either take a 2-hour sample that just for 2 hours sorbs stuff to that sample, you will average out the maximum amount, so you won't actually know what that is. Secondly, if you take a grab sample like happened in Los Angeles and you suck air into just a bag at one point and you send it to a lab, you could be missing the peak. So you may not know exactly what the concentration is. You may be getting data that is representative of the site, but not worst case scenario. Okay? So we took some of this condensate, the toxicologists that we're working with took some of this condensate, and we exposed it to mouse lung cells. And what we found is that there's 2 ways to read this graph. First and foremost, this is cell viability. This means the cells survived after 24 hours. And if it's less than this line, then that means they didn't survive. Okay? What we found is that some of the cells did not survive that were exposed to site 4 and site 5 condensate. Okay? 2 different sites. What we did find is site 1 and site 3 condensate didn't cause the cells to die. Okay? So there's likely operational conditions that can be used that wouldn't cause toxicity in the materials that are emitted into the air. Okay? We think future health impact investigations are necessary. So where we are today is pipes still need to be repaired. Some of the CIP technology has caused harm and impacted the environment. We're not certain about the frequency, the scale, or the extent of impacts because there really hasn't been a concerted nationwide study to figure that out. Public health and occupational health risks remain unknown, and workers and the public have not been appropriately informed about what the emissions are. So moving forward, we have some recommendations in terms of what needs to happen. We recommend that the federal government sponsor a study to investigate short and long-term health impacts for the general population that is exposed to these materials, but also for the workers that deal with this every day. You can create manufacturing conditions used to capture and eliminate emissions, and how should sites be monitored. Okay? So the dawn of this, right? We've talked about really heavy stuff here, the significance of a technology that it has amazing rewards and possible risks. Well, there's different classes and groups of people that can do something about this. And I can tell you already that there are very altruistic people in industry that are doing the right thing in terms of taking steps towards making changes to better protect themselves, their workers, and the public, because the technology is pretty innovative. In July of 2017, the state of California issued this. They issued an alert to all of their public works departments and health departments, warning about the potential exposures by the public due to CIPP technology. So health departments are starting to pay attention now about the possible risks associated with this technology. CIPP workers can ask for help right now. They can call NIOSH right now. They can email NIOSH right now. NIOSH will come in and do an evaluation of the work site, of work practices, and they do it for free. So there's really nothing stopping companies, employers, and unions to do this. Okay? Workers can also go on CDC's blog right now and read up on cured-in-place pipe technology and emissions and current practices. Workers can learn more by participating in a webinar. We have a webinar October 5th with NIOSH, the National Environmental Health Association, to talk about some of these risks with CIPP technology and how to mitigate their hazards. Okay? And here's that webinar. Engineers, Purdue is an engineering school. Engineers have a duty to uphold public health, safety, and welfare above all in the conduct of their duties. Many engineers take this very seriously, and I will say one engineer that I know takes it very seriously. There used to be a video up online where the engineer was there saying that the emissions are harmless, not to worry about it, and then after the study came out showing that the emissions are not harmless, we can't say that in all cases, they removed the video. Okay? So making sure that claims about emissions are correct, making sure that the emissions are all captured until we determine that they are not a health risk, and notifying current employees about the potential long and short-term health impacts. So in closing, where we are today is you may not be a CIPP worker, you may not be in the water industry, you may not be a regulator or health agency, but you are part of our social fabric here, and you live somewhere and likely have family and friends that live somewhere. So my advice to you is pay attention. Find out if CIPP is being used in your community. Request that they capture all emissions, that they are not released to the atmosphere or work site or up sewer laterals. And ask your local health department to participate in monitoring and understanding cured-in-place pipe processes. You can also contact your congressional officials, and I think this would be a great idea if not only health departments asked for this, but CIPP companies and industry asked for the National Institute for Occupational Safety and Health to come in to conduct an independent study of worker safety, because we all care about one another and the health and well-being of each other. We want to make sure that those persons are best protected, because we cannot rebuild our infrastructure on the backs of people that could be affected and not be around to enjoy it as much as we do. We also need to ask additional investigations to be conducted to understand these health impacts. Okay? So going back to the purpose of this presentation, right, is cured-in-place pipe technology moving faster than our ability to understand it? I don't think so. We understand it, but it has become widely used. 50% of all water pipes in the U.S. are being repaired by this technology. You probably can't talk to anybody in the drinking water, wastewater, or stormwater industry that hasn't heard about it. Okay? But we don't have a body of evidence that describes how to make certain that there will not be short or long-term health impacts, or how to prevent them. And our position has been CIPP is a great technology, it's innovative, it provides an amazing service, and can likely be used without endangering human health and environment if safeguards are instituted. In closing, there are over 30 people that contributed to this National Science Foundation Rapid Response Study. I have several pictures up here. And the amazing individuals, they're material scientists, they're toxicologists, they're environmental chemists, as well as many other people that are not here. Utilities, safety, all sorts of amazing individuals that contributed to this. And I'm just here to talk about it. So thank you very much for the opportunity to be here, and I'm happy to answer any questions.
We're going to open it up to some questions. My only request with the questions is wait till the microphone comes to you so that you can ask them. So that way we can get it all on the video so that people that watch the videos in a couple weeks can hear all the questions and your responses. So Kelly and I will run the mics to you.
Thanks for the presentation, very interesting. You talk about cured in place pipe. That's a fairly large category. You showed examples of steam cured. Apparently you use water, boiled water to do that, and UV lined pipes. Are they all equally bad? And then what can a vendor do to solve those issues?
So there are definitely three different types of manufacturing methods. What we see mostly today is steam cured is the most popular method. So when we conducted our National Science Foundation study, we didn't really get to choose what we monitored, primarily because of we were trying to schedule it in, and steam cured was the most popular. So that's why we chose to monitor steam cured. They all seem to be different. There's no head-to-head comparison of emissions. We could say visually UV cured CIPP doesn't emit water into the air, so therefore it's different than steam cured. We could say that hot water has different types of emissions, but we really haven't seen from an emissions standpoint what types of materials are emitted from each process, because UV would have different complexities associated with emissions than steam cured or hot water. Yeah. Thank you.
Well, thank you, Professor Whelton, for the presentation. My question will be related, if you have estimate more or less, how much will the cost increment if they capture the emission, or you have an estimate, or you have asked the industry why they are not forced to do that, probably?
So one utility I had heard from says it's about $100 a linear foot to replace pipes, and it's about $30 a linear foot to repair pipes by CIPP using, I think, steam cured process. So it would probably be different because the magnitude of emissions probably will differ between technologies, which would mean that you would have different costs associated with disposal. That's where we want to get to, is figuring out, how inexpensively we can do that, capture the emissions, or, we don't necessarily need to capture them if they're not caused in the first place. There's other ways that some of the faculty that I work with here are looking at, designing resins that don't do that. So, yeah.
Okay, so my question is, have there been situations where, chemicals released from the CIP installation, has it caused health impacts that, could hurt people? And if so, has anybody been, interviewed or documented, their, health problems, or has anything been recorded?
So the question was, have there been any documented health impacts associated with cured-in-place pipe installations? I'm aware of some people who have claimed to have been exposed and gone to the doctor, and the doctor has declared that, their physician or the ER has declared that it was due to a chemical exposure incident, and that was the only thing that happened to them that day. There has been no nationwide study to look at what the exposures are and what the consequences are of those exposures. One of the issues is that a mixture of chemicals is emitted into the air and possibly up people's sewer laterals and through air intakes. So So any study that's designed has to consider mixture effects and not just one chemical. Going along with that, there is a focus in at least the industry to focus just on styrene as the only chemical because it's reasonably anticipated to be a carcinogen. It may be that styrene's not the agent that is problematic. There may be other chemicals present that could cause adverse health effects. But more work has to be done to figure that out. There have been those, there's now 65 incidents associated with people leaving buildings, people complaining about symptoms, health symptoms and such. And I would say even those situations, and when they're sending children to hospitals, I think that's a line that indicates that possibly there could be health impacts associated with this. If they're long or short term, we don't know.
How are they solving the lead problems in Flint, Michigan? Are they lining them or are they replacing all of them? Do you know?
So I talked to the U.S. Public Health Service. I think it was the admiral or general in charge. She had asked what types of technologies could be used. I think they're talking about coating. They've also discussed cured-in-place pipelining, but they've decided instead to remove and replace the lead service lines and install copper. The high-density polyethylene pipe industry has a project on the side where they're trying to demonstrate that their technology is as good as copper. But primarily right now, they're just removing and replacing service lines with copper.
Got time for probably 2 or 3 more questions.
As you're saying, a lot of these corrugated steel pipes are starting to look like Swiss cheese, and they're pretty ripped up. Is there a limit to how degraded a pipe can be for the CIPP method to be implemented?
According to what contractors have told me, yes, but it's a pretty flexible method. So if you have a pipe and maybe it becomes an oval, or maybe it's a vitrified clay pipe that's all come to pieces, you can't really push a liner through there to displace some of this stuff. So that would be a situation where you couldn't rehabilitate with CIPP. The really nice thing about CIPP is you can put pre-liners in, which is like a slip tube first. So let's say if you put a tube in and you blow up the balloon, you might have bulges coming out the Swiss cheese. But if you put a pre-liner in beforehand, the bulges are limited, and when you have bulges, you can actually have resin loss going into the area, or you can have stretching of the fabric, which would result in decreased mechanical integrity. Yeah.
So then when the CIPP finishes its life term, do you just insert a new one, or what is the next step after that? Would you start pulling out pipes, or what's the
I've
the
thought of
next
that. Right, so you start off with a 18-inch diameter pipe and you put it on a CIPP and it extends it for another 50, 30 to 100 years. And then here we are 30 or 100 years ago, grandchildren. Do we do it again? Do we do it again? I think what you're going to see is technology innovation. So what we saw with the trenchless technology industry happen, the dawn of trenchless technology, something else could be there. Some CIPP companies would like that to remain, but it's going to be based on the hydraulic capacity, right? So hydraulic capacity and some other things. And what CIPP looks like in 100 years. Right?
One more question. Well, thank you so much. This has been really fascinating.